Our first session today on computer experiments. We've got two sessions, one before and one after lunch. And our first talk in this session is given by Hugo Maruri and Henry Wynn from LSE. I think Henry is going to start us off, and it's going to be a bit of a double act.
So firstly, what a fantastic conference. I'm absolutely delighted, and thank you to all the organisers. In no particular order, maybe David, Justin. Anyway, we're not going to give a tutorial on computer experiments, so I'm assuming that you know. All we're going to do is something very simple. It'll look complicated, in fact it's very simple. We have two types of model. Hugo will do the first type, I will do the second type. We're going to prove de-optimality for these types of computer designs, space filling, low discrepancy designs. Hugo's going to do one type, I'm going to do the other type. Don't ask the connection with Krieging, it's a bit more complicated. I covered it in the talk in week 1. So just think nice, pretty designs which fill up space. That's it. Hugo's going to do Haar and I'm going to do Fourier.
Well, thank you, Henry. Well, we are interested in sort of designs that cover the space, and that led us naturally to a special type of designs called low discrepancy sequences. And I'll be talking especially about one design, maybe not that new for now. It's called Sobol sequence. This might look a little bit mystifying, this sort of expression, but in reality it's not extremely difficult. And well, I'm not entering into the details how to compute the points here in this lecture, but if you meet me afterwards, we could do an example, and it's fairly straightforward. So it's just a sequence, an infinite number of digits, of numbers, sorry, and each number is expressed as an XOR bitwise operation. So here is just one example. The point of this example is just to show that as we proceed along the Sobol sequence, we are moving, including each time, more digits. So we are first with 1 digit, then we move into 2 digits, then into 3 digits, eventually 4 digits, and as we go along.
Can you turn the microphone on?
That would be handy, I think.
It's on the top.
It's on the top.
Hello. Everything I said to Henry just before the talk recorded, so as I was just saying, this is going, this is going each layer deeper in the number of digits. So that means that we are spreading along the space, but without repeating points. Now, this is just a dyadic fractions. Then, all right, there is embedded into a more general type of sets of points, which are expressed in base B. And the relevant property to remember is that for every interval, left closed interval, which this volume, you always contain, each of these interval of these forms always contains this number of points, which is BT points, as long as the intervals are of this form and have this fixed volume. That is a finite set. If from an infinite set, we can always take a finite set of points that have the above property, that is called a sequence. Why this is important? Because these sequences have low discrepancy. And what is this property? Well, just in words, think of the Kolmogorov-Smirnov statistic is as low as possible. So that is the distance between the empirical CDF and the uniform CDF. Well, this is just that. And Sobol sequences are just examples of sequences of points with this property, low discrepancy. But I'll be speaking mostly of Sobol, but there is much more than Sobol. All this coming from number theory, and well, they are named after the people that just produced them or described them. We can also do scrambling, that is permuting the digits. I'm not doing that, I'm just doing traditional Sobol. This is one example, 2 dimensions for you to see. First 127 points of a Sobol sequence, and the next 127 points, they look like a reflection, but they aren't. The right set lives on a much finer mesh than the first set. And when they just come together, well, they look again like a reflection, but they are not. And in fact, they are a Latin hypercube. Right. Now that was all about Sobol. I'll be speaking about the models we are interested in, and it's just hard wavelet. So this is just definition of a hard wavelet. Again, it is ended on, it is including the left point of the interval. And well, from a mother wavelet, which is the basic structure, we construct daughter wavelets, that is halving and shifting. So we have two daughters, and from each daughter we could have and shift, and then we have four granddaughters, and so on. The generation is controlled by the parameter k, and the shifting is controlled by j. So here we have the mother and daughters and granddaughters. The scaling parameter outside is just to guarantee that the area below is unity. So this is an orthonormal system of step functions. They are widely used, especially when we have to approximate functions that have discontinuities. Oh, that's it. Now, what sort of models we'll be interested in? Okay, well, it's just, this is a linear model. The terms in F will be wavelets. And the errors are just the standard assumptions about the errors, zero mean, constant variance, IID errors. Now, what sort of models will be in F? Okay, the most important is a hierarchical. Think of a family that has the mother, daughters, granddaughters, and so on, provided that it includes all possible wavelets within a generation, and all the generations up to a level n-1. Well, there is a sort of father around, which is the intercept, and that is as well in this family. Now, there are other types of models, which is the AM. Here we only have the m-1 generation, as well as the father, if you like, and the IM, which is an intersection of some AM models. Obviously, if we do the union. If we do the union over all possible values, then we get to a hierarchical. But this is a sort of, IM is an intermediate model. So let me just present a model having just the daughter wavelets, that is k equal to 1, and no father. So we do have the 3 points in the Sobol, and this graph is just the variance of prediction. So when we add the fourth point in a Sobol sequence, we get to the variance of prediction is constant and is equal to the number of parameters, one for each wavelet. So we are in the optimality land. We are at extra points, no longer optimal. We add another one, we go to 7, and when we add the 8th point, we are again in optimality case. So as this goes along, we are hitting optimality every number of points, of successive points in the Sobol sequence. And this is hardly surprising, as the boxes, the intervals I was speaking before, they have the number of points, the relevant number of points. So this is an example of a net, and this would be another example of a net. Now, okay, if instead of putting this graph, we just put just the maximum variance of prediction, and this is again another model, just the third generation, no father. So well, this is how the maximum value of the variance of prediction behaves. So for sample size 16, we are in optimality, then we are adding, the value is increasing, then it goes down abruptly when we hit sample size 32. This is all summarized in this table. I mean, it just, the basic property is the property of being a net. So well, these are just the models without father. These are models with father. And then we find that there is a sort of robustness in that we require less points when we are adding the origin to the Sobol sequence. So that ties up, and well, it's just that it becomes a net with a smaller sample size. Now these results, some related results have been known for some time. Thiers and Herzberg and other papers before have been dealing with optimality for HM models, only one variable, and using design measures. Now this is not coming out of the blue, because these digital nets have been used for integration of Walsh series. Right, so this is our result. That is for multivariate design, and then essentially this is just a product model. Maybe it's easier if we see an example. So in 2 dimensions, we have 7 subtle points plus the origin, and then all the models with hard wavelets that have this product structure that is either on one, this is just the univariate hierarchical Haar, or a product of 2 Haars, one in each dimension. Well, they are all optimal. Now this is, okay, this was 8 points, 2 dimensions, same number of points, more dimensions, the number of models increases, and this follows just this classical result of the number of points in this simplex going out, that they add up to k. But an important property is that these designs are also optimal for models that are non-saturated. So this is rather nice. As it increases, well, it is optimal for this number of models, either some saturated, some non-saturated, all of them product models. Finally, okay, what is the next step? Well, thinking of this Sobol sequence, when we have this number of points, is either a Latin hypercube or a nice fraction of a full factorial design. And now if we move out of the realm of Haar models and we jump back to our favorite models, which are polynomial models, well, we have found in a number of cases that these models are always identifiable by this subset. But well, we have to prove such a thing. And well, even the next bit, can such designs, these Latin hypercubes, Sobol if you like, now this is interchangeable for this sample size, can be optimal, not optimal when searching among the whole space, because that would be just pushing points to the borders. No, optimal when searching among all Latin hypercubes. So that's a conjecture, and that's future work, as well as optimality for models that include not the full generations and so on. You don't want this,
You're going to have to teach me how to work.
If you just press here, then, and this is for the light. Just press it, the light.
All right. Okay. So the next class.
He doesn't want.
No, I have a loud voice. Do you want?
No, it's for recording. It's not for.
Oh well, we checked with the we did check with the technician who said it was all right, but I defer to Stuart. Sorry. This is so. All right. Sorry. I apologize. Okay. So this is Fourier regression, and it's again another class of not wavelets but standard multidimensional Fourier regression. So they're sort of signal processing models fitting. If you're a signal processor, you might be interested in fitting Fourier regression, say, in 2 dimensions. So it turns out that not the models, the designs which Hugo was talking about, but these kinds of designs. You take a single vector, we're in D dimensions here, we take a single vector D and we take multiples of it, mod n. So it's as if you're on a torus, but if you get outside 0, 1, then you have to fold them back and come in again. So they're all of that kind. So there are what you need for these designs to be d-optimal for certain Fourier regression models is that you don't get aliasing. Now, it's not aliasing in the polynomial sense, it's aliasing in the Fourier sense, in the cyclic group sense. And what non-aliasing in that sense means that, to summarize it, certain linear identities involving the generators must not hold. This not is very important in the theory. So it's not that certain, like G1 plus G2 is equal to G3. It's like G1 plus G2 must not be equal to G3 in these generators. So in some sense, these generators have to be self-avoiding in order for the corresponding Fourier model to be d-optimum. So the proof I won't give into, but it relies on the fact that, simple fact that cos squared plus sine squared is 1, and that when you've got your design and you look at it, and as long as you stick a root 2 in the functions, you get an identity for the moment matrix, and it's exactly the same property that you find with Ha. It's that identity which makes it d-optimum. So here's a little example. Here, the generator, we got 5 points in 2 dimensions. It is a Latin hypercube. You're kind of ignoring the boundary here. And we've got 5 points, and you add this generator, you take another multiple of it. When you come to the top, you fold around on the torus, and then you finish off here. So this is 5 points. Notice that there's 1, 2, 3, 4, 5 parameters. Those who know their Nyquist theory, and I will return to Nyquist theory shortly, is that to fit a time series in 1 dimension, you need 2 m plus 1 points, 1 for the constant, what you refer to as the father, and 2 because you've got m's the order, and 2 because you've got cos and sine. So let's take, and that's the same proof as I said before. So the k in the general equivalence theorem is 1 plus 2 plus 2 is k, which is 5 in this case. Another example. Now here's a more interesting example. We want to estimate models with main effects and first order interactions. So there's some cross product terms I haven't put in there. What the cross product terms do for you in the Fourier case is you get the g's summed up inside the sine and cos term because of the exponential nature of the model. You're not multiplying like x1 times x2. It takes place inside the exponential, so it comes out the g's as being inside the cos and inside the sine. And okay, so in the Annals paper, which was referred to, we said, well, okay, the not conditions, which are here, none of these things have to be equal, you see. They all have to be distinct. So this is the not coming in, right? So what you do is you take these generators, you say, I'll have the first generator which does not satisfy, does not violate the not condition. In other words, the first violator, which is, for example, not the sum of the first generator, which is not the sum of 2 previous generators, for example. And you run the computer, and you come up with a weird set of generators. So if you use these generators, you stop at a particular dimension, use these generators, generate your torus design, and it's the optimum for that model. All right? So there's kind of self-avoidance going here. So what happened was, I took the Annals paper, put these sequences into a wonderful thing called the Encyclopedia of Integer Sequences. And it's not often in your academic life you nearly fall off your chair, but it turned out some of these things we'd done using a greedy algorithm with this not going on, must not do this, must not do this, turned out to be famous sequences. That's why I'm standing here giving this talk. So, so here's this sequence 1, 3, 8. So what did this turn out to be when I put it into the... okay, so before we do that, let's have a general notation before I give you the little bits of magic. This is a Fourier model. This says I want terms up to order m1 in one variable, m2 in the other variable, and m is the order of the interaction term. So this would be a full model, main effect within the full model. Okay. So what you get is when I put these sequences in, it turned out there was connections with some really quite well-known sequences. certain Diophantine things, some dynamical systems, the Cantor set, which will appear, some of you may know what, and Fibonacci sequences. Just from this greedy optimization we did with the generators. So this is going back to the case I had before. So here we have second order main effects, non-alias. So this would be like a quadratic main effects model in the polynomial case. One means I don't want them aliased. All right, so you run the greedy sequence, and you get this sequence. It should be really Gn. So Gn should not be equal to twice its predecessor, any of the previous, and you get this very strange binary sequence. Well, this turns out to be the Feigenbaum period doubling sequence. It's a fixed point of this mapping, and let me go there's a lot known about it, and let me show how the Feigenbaum system works. You start out with 1, 0. You start out with 1, 0. You replace 1, 0. Wherever you see a 1, you replace it by 1, 0. Wherever you see a 0, you replace it by 0, 0. And you generate this sequence. This is obviously powers of 2. And this says, what this means is you take 1, you don't take 2, you take 3, you take 4, you take 5, you don't take 6, you take 7, you don't take 8, and so on. So this is a binary representation of the numbers you take as your generators as you move along the sequence. Okay. Another one, which is the 1, 1, 1, 2, turned out to be related to things called magic integers, and very, very, very much related to a famous sequence called the Sidon sequence. In fact, when I was over having a beer in week 2 with the postgraduate students, one of their students over there was working on number theory, and their supervisor, whose name I fortunately forget, was working on Sidon sequences. Sidon sequences are sequences such that, are sequences such that all the sums are distinct. So this is not, you see, this is no two generators should have the same sum. This is what you need for the non-aliasing and the de-optimality, and it turns out to be a famous sequence worked on by many pure number theorists, basically. All right, and thank you very much to Hugo. This is the kind of sequences you get using the more Chewy generators, and you see they have this Fourier torus type of structure. Okay, Fibonacci. Well, the most obvious thing is to stop the generators interfering with each other. Is to take Fibonacci. You add the previous two together, and the result is so big that it's not interfered with any of the sums produced before. So Fibonacci leads to a polynomial. You can solve Fibonacci-like relationships, and you can get that the GD is basically a polynomial. Is a power of G. So that's just from standard work results on Fibonacci sequences. So this is the one. This is the punchline. So I've nearly finished. I'm going to finish with the Cantor set. So the Cantor set, you take an interval between 0, 1, you remove the middle third, and then for the remaining thirds you remove those, and then so on. You go on forever. It has fractal dimension, log 2 upon log 3. So that's what on earth has the Cantor set got to do with de-optimality? Well, this is the answer. So it's actually it works for a resolution 4 design. This means, to speak polynomial, it says that your quadratic effects are not aliased with any second order, up to second order interaction. So it's a second order. So it turns out by a remarkable so what you do is you take what is the Cantor set? Well, actually, it's not actually the Cantor set. We're going to remove the third third, not the middle third. So it's a variation on the Cantor set. If I had a point here, it would be the set of points left behind after you've done the extraction from the Cantor set. You remove the point, flip it round, you then have integers. So these are integers in ternary, so the integers to the base c, but which do not contain 2. It's fairly easy to see that if I add 2 of these up, if I double a sequence like that, I get, like, if it's 1, 0, 1, but I get 2, 0, 2. But if I double it, but if I add 2 up, I must have a 1 somewhere. Otherwise, they're the same. So you can see almost immediately that these as integers have the property that adding 2 different ones up cannot be the sum of the second, and that's the Cantor property. And if you take the actual generators, you take 1 plus 4d times cd3, which is the Cantor case, and the general case. If you do this trick, so GD is 1 plus 4 times one of these integers, and that's the 1, 3, 4, 9, 10. That's exactly the algorithm, what we found using on the computer, using the greedy method, before we even knew where they came from. So it's almost done. Some general, so there's a, so this is a space-filling Fourier lattice derived essentially using properties of the Cantor set. Now this is a bit of extra for me. So what we really like is to go back to that time series point that I mentioned. We've got to choose the sample size n, which has been neglected all this time. So you've got to choose n big enough so that mod n, we have all these knots working for us. So there's a general way of setting this thing up, and then we ask for, then the cheap way of doing it is just like a one-dimensional time series. There is a number m, which might be something like, it could be the biggest, m could be the biggest quantity we get from those Diophantine equations we wrote down, and that's then our Nyquist number. So, so finally, in this theory, we can use greedy algorithms, which have good asymptotic properties. Hopefully, we can find a recurrence which does the greedy, or we could do optimal non-greedy. We could find that literally the minimal set of generators. But that's a lot of computational power. And that's it. Thank you very much.
Okay, time for questions for Henry and Hugo.
Henry?
Yes.
I'm getting quite excited because this is another connection. These sequences that you find,
Yes.
I know them under the name sum free set.
Simply, yes. In fact, on an original version of this, we had that phrase.
Okay, so you're aware of the literature that
Yes,
calls them sum free sets. Okay.
Yeah, yes. It's they're a special case of some free sets.
Yeah,
The
right.
Sidon ones are.
Yeah, okay.
And nobody, there's famous conjectures to do with them.
Yeah, sure.
Okay. So, yes.
If you're doing a design for a computer experiment, then
Yes.
you use a Sobel design generator or the Fourier?
Well, there's still research to be done. Because there's a note to go back to look at Niederreiter's work and where we probably find that the net properties, the very really strong net properties, which a Sobel sequence have, produce low discrepancy, but that's only for integration. So, which you use. I mean, I know that we worked with Ron Bates on this, and what he was doing is he was, even among the list of generators we got, we would pick generators which had good projection properties. So I would say Fourier is very easy to generate, but just be careful that you pick, even within the good generator list, pick good generators. And then I think they're pretty well okay compared to other sequences, and they're very fast to generate. So.
May I just add that, well, it's just really hard to say. I'm not really saying that Sobel would be like a one-size-fits-all, because even if it is multidimensional, you need to have a look at the, let's say, at the lower dimensional projections to see that they are still all right, even being a Latin hypercube in this extremely high dimensional space. But the advantage of Sobel is that you can still add points. So you take the first Latin hypercube and you carry on if you feel you need to.
Right. We'll fight it out between us.
How much are things different if you don't have square? we have another region. For
Very
instance,
good.
triangle. This might come from your knowledge that response function is symmetric along the
Okay.
diagonal.
There's two methods. You can do it by rejection, right? You just pick the member of yours, so put the region inside the big rectangle, just take the ones in the region. That can be very expensive because often these strange regions have very, very low volume compared to the hypercube, right? The other point is where that region you're talking about is an easy transformation of your previous region. Okay, so the third possibility, if the region is star-shaped, if you go back to Brad's wonderful talk, when he was doing quadrature, if it's star-shaped, you put a point in the middle, and you look at somehow do some sort of spherical space filling related to the fact that the region is star-shaped. Those are about the three ideas we've had, but it's tough. The fourth idea is to bound your region in something easier. So there's these minimum ellipsoid things. You put a minimum ellipsoid, then you distort. You can kind of transform the sequence onto the ellipsoid somehow like that. So there's a few techniques around for handling that, but none of them particularly satisfactory.
Let's thank Hugo and Henry again.